Okay, today we're looking at collision theory and Le Chatelier's principle, and basically how the basis of Le Chatelier's principle is deeply rooted in collision theory. So our syllabus outcomes explain the overall observations about equilibrium in terms of the collision theory, and examine how activation energy and heat of reaction affect the position of equilibrium. So let's have a bit of a refresh. So these are the answers to the revision questions from last time. So if an equilibrium system is disturbed, then the system will move to minimize the change. So that's the basis of Le Chatelier's principle. If a chemical is added, the equilibrium will move towards the side away from that chemical. So again, if a reactant is added, it'll move to the side of the products. If a product is added, it will move to the side of the reactants. If the pressure is increased, the equilibrium will move to decrease the pressure by moving to the side with fewer moles. If the temperature is increased, the equilibrium will move to the side that lowers the temperature. And remember, all of these work both ways. So decreasing the temperature, it will move to the side that increases the temperature. Now, all of the chemical system behaviors observed in Le Chatelier's principle can be explained using collision theory. Okay, well, at least the adding and removing of products and the change in pressure and volume. Change in temperature is just deeply rooted in thermodynamics, and we're not going to do that today because we just have to look at collision theory, but it does have a thermodynamics basis. Now, remember, collision theory states that for a chemical reaction to occur, there needs to be a collision between molecules with the correct orientation and enough energy. More collisions equals faster rate of reaction. So what happens when we change one compound? So imagine when we add a chemical to or remove a chemical from an equilibrium system, we're altering the number of collisions that that chemical can undergo. So if we halve the number of molecules in a chemical system, then we halve the number of collisions that can undergo and effectively halve the rate. Okay. So let's look at an example using this reaction. So it's our good old sulfur dioxide and oxygen gives us sulfur trioxide. Assume that the system has already come to equilibrium. We have those constant concentrations and those equal forward and reverse rates. But we go and ruin it all by adding some oxygen. So when we add some oxygen, what happens? Well, there's now more oxygen in the system. If there's more oxygen in the system, there are more collisions involving oxygen, which increases the forward reaction rate. So now the reaction rates are not equal. We've gone and changed that. Now, adding oxygen doesn't actually affect the reverse reaction rate at all. It doesn't do anything. But we've increased the forward reaction rate. So we've unbalanced them. So what happens is the reaction then shifts to the side of the products. How does it do that? Well, as the reactants are used up, the forward reaction slows. As more products are formed, the reaction rate of the reverse reaction increases, and then it comes to this new equilibrium. Okay, we get to a new point where the forward and reverse reactions are equal. Now, they're not necessarily going to be at the same position they were before because we've changed the equilibrium system, but they will still be equal. So here's an example. So here we have carbon monoxide and water producing carbon dioxide and hydrogen gas. So we can see that, if we put carbon dioxide and water, carbon monoxide and water into a reaction vessel and allow it to come to equilibrium, then we're going to get some forward reaction happening. As the forward reaction occurs, it's going to reduce because it's producing products. Some of the products are going to also become reactants again, but it's slowly going to come to equilibrium at this point. So this is the point where it reaches equilibrium. We leave it there for a little bit, and then we've gone and ruined it by adding some water at this point here. Okay, so suddenly the concentration of water increases, which also suddenly increases the rate of the forward reaction, so it jumps up. And then the same thing happens. So it slowly reduces, and the reverse reaction slowly increases until we get equal reaction rates again. Now, like I said, they're not necessarily what they were before, but they are still equal. Like the rates of reaction are now equal. Now, what I said before, that also works for the opposite way. So if you remove it, suddenly there's less of that stuff, less reactions occurring. We've reduced the rate on the side that we took stuff away from, and so the other reaction rate is faster. And so they're going to swap, 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 swap until the reaction rates are equal again. Now, changing pressure. Why is it that when we increase the pressure, it goes towards the side with fewer moles? Well, let's again take our sulfur dioxide, oxygen, sulfur trioxide system and assume we've gotten it to equilibrium, but then the pressure is increased. Well, what happens? We know from Le Chatelier's principle that if we've increased the pressure, it's going to want to go to the side with fewer number of moles, so it's going to want to go towards the products. But why? Why is this happening? Well, the increase in pressure results in an increase in concentration of both the products and reactants, meaning that more collisions for both the forward and reverse reactions are happening. But the reaction rates and the successful collisions are what we call multiplicative. Okay, so they multiply. Basically, in this example, and this isn't going to happen with all of them, it's just this specific example and that these numbers are useful for. Each other one's going to be a bit different. But for this one, if we've doubled the concentrations, then the rate actually increases by 2 to the power of n. Okay, where n is the number of moles on each side of the reaction. So for this one, we have 1, 2, 3, 3 moles on that side, but 2 moles on this side. And so what we're going to find is that the forward reaction rate goes up by a factor of 8, but the reverse reaction rate goes up by a factor of 4. And so because we now have an imbalance in reaction rate. An imbalance in reaction rate means it's not at chemical equilibrium. So the one that's higher is going to slowly decrease, the one that's lower is going to slowly increase until we get that equal reaction rate again. Okay. Now, why is it? Why is it that increasing the number of moles, increases the collisions? Well, let's assume that we have a box. So this is just a simple area with 2 molecules, 2 reagents. For those to react, they've got to collide. Okay, so there's just one possible collision there. Now, if we doubled the pressure, so it's effectively doubling the concentration, we now have 2 molecules of each of the reagents in that vessel. But now there's not only collisions that can occur between these ones, but they can also occur that way. And so where on the left we had one possible collision between 2 molecules, on the other side we have 4 possible collisions between 4 molecules. So we've doubled the amount of molecules, but we've quadrupled the number of possible collisions. So effectively we've quadrupled the rate. Okay, summary. So collision theory is the main driver of Le Chatelier's principle. An increase in collisions causes an increase in reaction rate. Unbalanced reactions then need to balance to restore their equilibrium. And reaction rates will balance out after a system is disturbed. Okay, so what I'm going to get you guys to do now, we have another modeling task similar to the dice, but we're going to be using a calculator and some M&Ms. Okay, so we're going to set up like we did before, we're going to take some products, move them to reactants, take some reactants, move them to the products. But then what's going to happen is you're going to reach a point where you're going to introduce some more to one side and see how the rate affects that. Then what you're going to do, once it establishes a new equilibrium, you're going to take out a bunch of those M&Ms, you're going to eat them so you can't put them back into your system, and then we're going to do the same thing again. We're going to take a proportion of the products, move to the reactants, take a portion of the reactants, move to the products, and watch that dynamic equilibrium establish yet again. Okay, so that's all for today. Thank you very much.